Welcome back, people. After 3 weeks, finally another video. I finally did get a fiber optic installed at my home, and the internet speeds are insane. I'm so happy with it. Okay, so let me make myself smart. Yeah, that's correct. So today we're going to try to make Dall-E. Um, This is the recent OpenAI paper. I think it came out a couple of days ago, January 5th, one day after my birthday. And it's insane. It's ridiculous what this model can actually do. It's like you give it text and it's able to generate an image out of it. It's brilliant. Just look at this. An armchair in the shape of an avocado. So on this website, they do give like a ton of examples. What's most insane is this temporal knowledge piece, which is I think the last one here, and it has an understanding that varies over time. So I'll just show it to you. Picture of an action movie poster from 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 different time, from like the 1900 1910s, etc., etc., and somehow it is able to capture some information about the data, and so you can see the kind of things that it's producing. Magazine cover, for example. Just look at this. It's insane that these things actually work. And in case of future, a lot of time only the text future is, they just write text. For example, 2010s, it thought I have to write 200 20. It wrote 2001, which is quite fucking insane that they're actually able to get a model to do this. From 2000 is a blank copy. I don't know why. 2010s, 2005, smack in the middle of it. Television from 1900s. Now there was no television. Was there? Wait a minute. Television. When was television actually invented? Late 2019. Sorry, late 1920s. So in 1900s, this is what the television. This is so amusing. It is insane that a model can actually do this. Or television or phone from 2000. Look at this. For the phone piece, it's actually very, very smart. That is actually very smart. Wow. In the future, we're still using this, whatever this is, or this. And today just showed it the back. It's pretty neat. It's very, very neat. Geographic location, it understands a couple of things, mood lightings, etc., etc., etc. It's able to understand all of this. Food from China, food from nice, India. Oh, dal talka, gajab. Food from the USA, maybe. What is it? Burger. This is not food. This is stupidity. Sequence of geometric shapes. You can also give it an IQ test, which is absolutely fucking insane. It's absolutely fucking insane that this thing works. Ridiculous. Whatever this is. This is neat. This is super neat. Green and bomber jacket. and black navy sweatpants. Fucking works, man. This is. Anyways, so what we are going to do is we are going to try and build our own shed, but with a little bit of difference. Now, what I've been really thinking about is the next GPT is going to have the image support. It's just inevitable. I mean, how much more can you do with text? They have demonstrated the absolute limits of text. The next model, the next GPT is going to possibly going to take in images, and it's going to be a mixture of it. So it's going to work like, what is this, and this is going to be the image, and you can feed it the image piece and it is supposed to, for example, create a description of what is in this image, kind of thing. And so we are going to try and do that, but I did look into a lot of it. I thought we should be able to do Coco data set, but the data set is like 16 GB or something, 13 GB, 6 GB. I mean, we don't want to do any of that. We want something much simpler, easy to understand thing. And by the way, they also came out with something called Clip, which is also very neat. Now I did try to download the ImageNet dataset, but it's like, if you have a freely available email ID like Gmail, Yahoo, what was it, Hotmail, then we are going to outright reject it. What the fuck? I don't have an edu kind of email. Do I need to like create temporary email to actually get access to it? Just again, stupid. This is their, I don't know why they're doing it. Why not just publicly release it? What's the big deal? Coco is like, it's 13 GB, 19 GB, and they allow a public utilization of it. Do you think it's going to stop people from stealing a data set, not using it for commercial purposes? Of course they're going to use it for commercial purposes. Where the fuck do you think they're going to get the data for it? It's insane that these companies think that, writing things like, please do not use it for commercial uses, it's actually going to stop people from using it. It's such stupidity. These people are insane. I don't know what they think before they actually start working on these things. Stupid. Alright, so first let me close up a lot of my work. And Dall-E ImageNet, no, we are going to do simple Dall-E baby. What happened when Dall-E was a baby? When Dall-E was a baby trained on Sapphire. Yeah, git ignore. I want git ignore. I anyways have to add shit to it, so no, fuck it. Okay, let's start. Dall-E baby. First is this, and the second is we're gonna start a Jupyter notebook. Yeah, so let's go to the Jupyter notebook. See, I release my shit in MIT. I know no one is going to read it, but if anybody wants to steal it, they're going to steal it anyways. I mean, man. From Torch Vision import datasets. How does it work? Alright, datasets dot Sapphire. No, I want Sapphire 10, and root directory where the dataset is stored. Root is going to be this thing. Let's just create a folder called, oh god damn it, yeah, Let's just create a folder called data, and if true, creates a data set from training dataset, otherwise creates from test dataset. Train is true. Transform. Yeah, we should define all the transforms, right? Transform that takes in a PIL image and returns a transform image. Yeah, for now, just let it download this thing. Download is equal to true. God, the speed, man. I love the speed. I mean, I don't think I'll ever be able to go back to pre-fiber optic. I mean, this is insane. So happy with the speed. This is Sapphire. Alright. Let's take a look at what Sapphire looks like. It's going to extract into shit. Okay. Dataset Sapphire 10. Number of data points is this. Sapphire 0 gives me PIL. Oh my god, it's actually so small. PIL and a class. Okay. Lens Sapphire. 50,000 images. Okay. Sapphire is this. I do PLT. Oh, I need to import things from import matplot lib dot pyplot PLT matplot lib inline, and I then do a plt.im show Sapphire 10 0. The fuck is that? Oh, now I see. Interesting. And where do I get the class objects? So is it something Sapphire dot class to idx? Oh, this is super class. A Sapphire 100. Oh, is Sapphire 100 bigger? This is a subclass of Sapphire 10. What is Sapphire 100? It has 500 training images. Do they have the same images? Sapphire 10 versus Sapphire 100. Oh, we have a class of overcoming new barriers which needs to be open. Sapphire 30 by 30. Oh, so the size is also different. Sapphire 10 has 60,000 30 by 30 color images and 10 classes, means 6,000 images per class. The dataset is divided into one test batch and 5 training batches. Each batch contains 10,000 images. In the test batch, there are 1,000 images which are randomly selected from each class. Let's see. CFAR 10. Okay. CFAR class to IDX. You have much larger number of classes. What else do we have in CFAR dataset? CFAR. Okay. So I have CFAR 100. God damn it. And I have CFAR 10 datasets. Let's use both of them. It's not that big of a deal. What is lens CFAR 50,000, CFAR 10, and lens CFAR 100, 50,000. And so what we're going to do is we are going to create our own simple wrapper data set of these two things. So from our torch.utils.data import data set. Okay. And our class CFAR I'd like the images same. CFAR same images. CFAR 10 variants of these data sets. File names. So let's just assume that is not true. So for example, let's just use this for visualization. For this and CFAR 100. Alright, so at least the values don't match. Cool. So class CFAR wrapper dataset. Oh god, dataset def in itself. There's nothing like that. Self.c10 is equal to datasets. Oh wait, no, that's fine. Cool. C100. Cool. And if len is equal to self return len self.c100 plus len self.c10. This is CFAR 10. Do we need a different test? Yeah, let's just keep it. Let's keep test different for now. Get item if I less greater than len self.c100 return max of I minus 1 I is equal to I minus len self.c100 Yeah, you know what, fuck that. If I greater than len self.c100 d is equal to img is equal to self.c100 c10 50,000. No, let's just also keep it abstract. Len self.c1000 I minus, and this is the image. Class is equal to self.c10 b sifar 10 dot classes. Cool. 10 dot classes d d1 img is equal to d2 d0. Is there some kind of an augmentation to perform? I do not know. Else and this is just this thing. 700 if I greater than self, if I greater than c100 return from c10. Simple. Cool. And all I have to do is return img and d, no, cls, right? Sifar is equal to sifar train, and I can just do this 9. Fuck me. Print wait. Elephant. Now I need to create a random string for this particular image. So the idea is like this. We are going to ask it questions. Please create a photo of an elephant, and then it is supposed to create a photo of an elephant from this particular from the Dall-E system. Then for that we need to perform a couple of things. First is we need to train a discrete VAE. So using discrete VAE we can convert our pixels into very dense number of tokens. And the second step is going to be to actually generate a lot of synthetic text. So the first thing we'll do is we're actually going to train a discrete VAE. So let's start by reading the papers that these guys have mentioned on the blog post. It goes from 9, 10, 11, 12. Yeah, so this, and this. Okay. Auto encoding variational bays. Bay. Are you my bay? Will you be my bay? Alright, so this paper is most likely going to be the variational autoencoder paper. Autoencoders are super simple. Compress it, add some noise, return it back. Simple. No fucks given, people. Other than that, I have no fucking clue what actually happens in this paper. Like I should probably read it. Solution of Kubrick Leiber divergence cushion case. Now you can simply demonstrate that the cubic divergence is basically this times log plus this into whatever is the standard the mean minus the standard deviation. So 1 plus standard deviations blah 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 blah. When using the recognition model, then mu and SD are simply functions of S and variational parameters phi as exemplified in the text. 2D latent space, 5D latent space, 20-dimensional latent space. Let me just text someone. Man, this is a pretty good learning experience. Pretty decent learning experience, I would say. So you take a mini batch version of auto-encoding variational base. Either of the two SGVB estimators in section 2.3 can be used. We are using setting this and this in the estimator. Initialize parameters, random mini batch of this, random samples from noise distribution epsilon. You calculate whatever is the gradient from theta, phi, xm is the mini batch, and epsilon is the random noise, and you update the parameters based on SGT or add a grad. Cool. That's the basic idea of this thing. Oh wait, there was one with the faces. I want to see what happens with the faces. Freight face manifold. There's parts of pose. So okay, so it learned the pose part, and it also learned the how to show teeth part. Stochastic backpropagation and approximate inference in deep generative models. We marry ideas from deep neural networks and approximate Bayesian inference to derive generalized class of deep directed generative models. And oh my god, what are these guys trying to say, man? Man, what are they trying to say, man? Yeah, I don't understand shit. Too stupid for this industry. I'm too stupid. Too stupid. Gumble softmax. And the concrete distribution, the continuous relaxation of discrete random variable. This is this paper. This is I think the paper that deals with this piece. So we'll first see what the image that these guys. Okay, so there is nothing here. I'll explain what happens here very briefly. So what the piece that I understood was you take in an image. So the first problem is how the fuck do you actually compress an image and feed it to a transformer? So now you can use a VIT style system, but then the problem is that you are now supposed to be generating in a continuous distribution instead of a very discrete distribution, which is what happens in case of languages. What I mean by that is that you would transformer you would like to predict a very specific token. Now there are different tokens that can actually be used. One way is what was used by Andrich Karpathy in MinGPT. What happens in MinGPT is he performed a k-means on the entire CIFAR10 dataset and finalized 512 tokens and decided to predict based on only on those 512 tokens. This is a super smart way of doing it. In fact, it's so smart that if you have any set of continuous distributions that you're unsure of what to do with, you can simply pass it through a k-means clustering algorithm, determine your k values, and basically see the kind of loss that you're getting. You should also visualize what different clusters are for. So for example, if you are given an OCR, what you can do is you can perform k-means clustering on the entire data set of all the coordinates. And so if you're given any coordinate pair, that is x min, y min, x max, y max, what simply all you have to do now is pass it through the k-means clustering, and it will automatically tell you that, you know, this particular cluster is the closest match to your location, to your bounding box. More on that later. I mean, that's not the point here. So the first thing we'll need to do is we'll need to implement a discrete VAE. God, I can't images, man. I don't want to show me. Oh, show me, I want images. Yes. So you have something called VQVAE. Now this is the idea that given any particular input image, you compress that image, you pass it through a CNN, and then you get a very discrete set of tokens. This discrete set of tokens comes from the embedding space that is here, and whatever value is predicted, you simply predict what is the nearest k-means. I think it's k-means distance. I would assume so. But all it now has to do is it has to predict whatever happens in the nearest embedding, and it's going to assign that value to that text. So you can create a continuous distribution to an embedding space, and then all it does is that it goes around in the embedding space and tries to find what is the closest. So loss is basically the embedding space learns continuously, and simultaneously through this kind of a loss you learn the autoencoding loss. And so what happens is your embedding space, it also automatically learns what are the coolest what are the best representations of the text, and simultaneously you also get the discrete output from variational autoencoder, from an encoder, text image encoder basically. So I think this is the VQA paper. Let's see. Just one dude. Respect D-Wave systems. Is this the paper? Is this the paper? I don't think this is the paper. It's a pretty damn big paper. What we need is we need to implement VQVAE. Vector quantized. Just a minute. I don't understand shit. I understood this piece. Yeah, so let's just try to implement this thing. First is the first step we need to do is that we'll actually need to train the VQVAE, and once that is training in the background, then we'll start to code the language part, and that is also going to be fun because we'll also try to introduce paraphrasing and other cool things in it. All right. So first is from torch import, and then from, and just import torch. Cool. So you have class discrete VAE, and what it is, you have this is nn dot module def in itself, and what I need is what is going to be the hidden dimension of this thing, and the number of tokens that we are also going to be using. And so the next thing what we need is we also need the num layers. So you're first going to have encoder layers. So for I in range num layers, what do you have? God, I'm super bad at this thing. n.const2d. You have the, what is it? Okay. So these are the 4 things I have. God damn it, mine. I told you, my. By the way, I started watching a series called Hung, and damn, that's one good series, man. It's funny. This is going to be hdem, except for the first layer. Hdem if I greater than 0, else this is going to be 3. It's hard coded. This is always going to be hdem. Kernel size, let's just keep it at 3. Stride is equal to, oh fuck, padding is, this thing is 0 is fine, and dilation of 1 is also fine. And then what we need to do is enc dot extend enc layer, and also we need the ReLU this thing. We do the same thing for deck, except it's continuously hidden. Cool. So this is deck layer, and just like this you have decoder layers, and you have decoder layers, this thing, and this thing, and so yeah, that's it. But this is wrong. I need help. I saw this dude, he wrote some code. I'm probably going to use this one. So what is he doing? He first has encoder layers, decoder layer, padding. Okay, so kernel and strides are changed. We'll play with it and then figure out. And encoder layers, so it has to the number of tokens. And cool. And so codebook is simply an embedding dimension. What you do is so you have a different function for decode. What happens is you can pass it, you first pass it through a self-encoder, and you create a sampled, which is an INSA. What that means is the NN, it goes away. Simply get the D, self one hot. Okay, you have the self codebook dot weight. Okay. Okay, got it. I got you, man. I got you. Got you. You have decoder. Otherwise, you simply return what is an MSC loss. Wow, MSC loss? That's something. Okay, let's implement this thing. So for Dall-E, why is he implementing clip for Dall-E? Well, people do crazy ass shit. Yeah, so now we also need to add encoder layers dot append and then dot conf 2d and in channels is equal to hdem, out channels is equal to num tokens. Yeah, let's just kernel size is equal to 3, for example. Okay, fine, whatever mate, whatever. Decoder layers dot append. What did this dude do? This dude later converted to 3. Cool. So I don't need this. It's always going to be hdem. And what he does is that he fucks with people. Get it? He fucks with people. Conf transpose 2D, right? Don't need this thing. You need to scale up the image. That's why you need a conf transpose 2D. And then you finally have this thing. And now you'll need the kernel size to actually be 1. This is 3. That size. And self.encoder is equal to nn.sequential star encoder layers. Self.decoder is equal to nn.sequential star decoder layers. Self.codebook is equal to nn.embedding. The size is num tokens and hdem. Cool. Def forward. What forward does is, oh god damn it, self x, and then simply enc is equal to self dot encoder x. Then we need to find the god damn it, let me just close the window. These fucking kids, man. Okay. So now we need to perform an operation, and this is neat. We are going to use INSA, nothing else. INOPS is, it's ridiculous how good it is. INOPS, oh, there is no INOPS. Pip3 install, oh no. what do we have in Inox? And let's just use Einsum from here for now. And we are going to do Einsum, which is head tokens is equal to Einsum. Einsum is you have breadth, channels, width, height, and you have another matrix with shit. You have channels and dimensions. We didn't do this. We need to perform the Gumbel softmax. Soft one hot. Okay. Soft one hot. F dot import tarch dot nn dot functional as f. I also need to study what is Gumbel softmax. So f dot Gumbel softmax. Okay, so what if I have a tarch dot tensor and the values were like this: 0 point minus 1 point this plus 4 point this thing, except 0 point is this, have 0 point this, and you have 3 point this. Here x is equal to this, and here x this. Okay. So clearly this thing is the most favored one. It does not give you the exact weights though. That's the problem. It sent it to a decoder. Anyway, you get the Gumbel softmax. You have the encoder output. Send it here, and what this thing is saying is you are going to get this into num tokens, and you have num tokens cross dimension, and what we need is to replace simply DTWH. Cool. And also going to perform the operations. So soft one hot and the codebook, which is soft one hot and self dot codebook dot weight, and out is equal to self dot decoder times header tokens turn out. And so you have m model is equal to discrete VAE. HDEM is 16. You have number of layers is equal to 3, and number of tokens is 128 in channel. Cannot assign module before init call. Oh, sorry. Super init mind. Okay. What is model? Does this work? Model tarch dot rand n r torch dot random, and I need to give it the size, which is 1 cross 3 cross 32 cross 32. And what is the output size? 30 cross 30. Man, I don't understand shit. Should we just use the values that these guys were using? I know it's cheating, but I can't do shit. Padding is equal to 1. Now we're supposed to get some good output. Same output. Asshole. What an asshole. Kernel size is 2. 32. What happens is 2. 33. 32. Cool. The kernel size here is 3. Stride of 1. Cool. Now we're getting it. We got it, bitches. Model dot this should be something about the number of parameters and operations in total. $32,000. Cool. Cool. So you have this thing, and now our aim is to train a discrete VAE class. Discrete VAE trainer def in itself model path I first need to initialize the Cephar train dataset. Cephar train. Define the dataset. Next we need to train dataset transform, and for transforms we'll need to apply something just from torch vision import transforms, right? img transforms.compose of transforms dot to tensor transforms dot normalize, and Cephar 10 mean end, Cephar 10 mean and std. Yeah, this is what we need. I'll be back. I need to go to the washroom. PyTorch tutorial. Welcome to PyTorch tutorials. What do we want to learn today? We need to perform adversarial examples generation. We don't need to perform this. Torch vision object detection dataset. Cool. Then what you have is get transforms. Random horizontal flip. First is this thing. Random horizontal flip. We should augment this dataset a lot. That is true. Transforms dot random horizontal flip. I want to be performed by p is equal to 0.5. Then transforms dot random. What else do we have? Random vertical flip is also fine. P is equal to 0.5. Then you have transforms dot lambda normalize random affine. Just a minute. I'll use one I have been using some time now. Which is, I have been using it for human pose estimation. Yeah, resize. Oh, I should add resize function. I'll be fucked. Resize this to 32 cross 32. Also, what is the shape of this thing? I should have probably print this so I know. Asshole. Where's the size reduction? No, mate. No. Doing something wrong. Kernel size 2. Oh, shit. Kernel size is 3. It's 24. No. This is just wrong. What did this guy do? Oh, so dim is like this particular value. Stop playing with my face. No. This is just wrong. Padding here has to be 0. 1 times this. Stride of 2. Stride cannot be 2. Padding needs to be 1. Padding is 0. Still give me 21 cross 21. No, I want it down to 5 cross 5. Layers. Number of layers is equal to 5. What do I get? 15 cross 15. 58,000 parameters now. 15 cross 15 is what? 125. No, 155. This is 175. No, yeah, well, something like that. 225, sorry. No, it's still pretty big. No. Ten cross 10. Hmm. Stride is equal to 2 if I greater than 0, else 2. And let's see what happens here then. Hmm. 100,000 parameters for this thing, 83,500 parameters. I think that is a pretty doable value. It's going to go down to 3 cross 3 and I don't want that, so let it be 3 cross 3 is like, it is too small. 8 for the 5 gives 15 cross 15. 6 gives us 12 cross 12. 7 gives us 9 cross 9. 9 cross 9 is 9 cross 9 is pretty doable. We already training models that are like 180 tokens long. So if you have 180 tokens long model, you can possibly afford till 12 cross 12. So let this be 5. No, let this be 6. I have 12 cross 12. Okay, this is our final value, and embedding dim is equal to encoder layer's final value is equal to embedding dimension, that is true, but this thing, if I is equal to 0, else h dim. Embedding dimension is 512. That means is I have got 16 channels instead. First up, let's also nomenclate, give these things values. It's getting pretty big, I'm getting confused. This thing is 128. Number of layers is equal to 6. Number of tokens is 512, and embedding dimension is equal to 256. Cool. So now the Gumball softmax is giving 512 values. This I believe would also be the same, which is enc.size. Yeah, so it's going 512. From 512, what we have told it, it's stuck at Einstein. No. Oh, it's already hidden, tokens already done. Hmm. 512 was. Oh, wait. This thing is actually. Okay, perfect. So yeah, innermost value is 112 cross 144 cross 512. Cool. And let's just give this the fixed values 128. Num layers is equal to 6. Num tokens is equal to 32. Embedding dimensions is equal to 64. Embedding dimension is equal to 256. No, wait, we can have a very big vocabulary, right? Sorry, and number of tokens is always much larger. So you can have like 1024 tokens here. You can have 1024 tokens here. It's already a 4.5 million. God damn it. 4.6 million parameter model. No, it's too big. Come on, Mike, come on. Can't have model this big. 28. Yeah, that's much closer to heart. Your transforms. What else? What else do you have that can that I can enjoy? Zero. Cool. Cool. Cool, 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 cool. What values? Should I use the ImageNet values that I have been using, or should we use some other values? We'll just use the normalization for ImageNet. No, let's not use anything. Def train. So for training I need values like batch size. I need to get the model, and I need to parallelize the model if needed. And so the first thing I'm going to do is I am going to configure my vast.ai machine. Let's use pretty decent machine today, not just one 2080. How about a 3090? Yeah, let's just use a 3090 today. We'll also need to copy all these values into a file, which is discrete VAE, discrete VAE trainer. Oh, that part. Okay. Now the first thing I have is I have these FR data sets, and I need to correct the indentation. Indentation, you bitch. Alright. So this is done. And what else? We need the trainer. Okay. And now we need to simply copy paste the values. Import, sorry. Cool. File code to train a discrete VAE. Cool. Model. And we do rest of the things with model like we would train the rest of the code. So I'll just open the chess.lm thing, AI chess.lm code. There have been huge improvements on this end, on this front, sorry. Now we need to include the GPU shit. Why? because, well, have to do some things in life. There goes my laptop. Self-chart model. Oh, I already assigned it here. Self-chart model is equal to model. Cool. And now a save checkpoint functionality. It saves the values at the given path, and then what else are we left with? Next we need to write the train function, that train, what do you have? Self model is equal to self dot model, and train data is equal to self dot train data set, trans is equal to self dot transform, and then what you do is you need an SGD. So you have an optimizer in this case. It's an SGD optimizer. You have torch.nn.optimizer. Oh, where is that dude's code? We're just going to copy paste this dude's code. What? Yeah, I'm going to copy this dude's code. Dude. Dude. Come on, dude. Nah. Nah, fuck it. We'll also need to write the code for loss, which in this case is going to be loss is equal to x dot f dot msc loss, which is out times x. What you need here is soft 1 hot and last. These are the two values that you get from this thing. Optimizer optim.sgt optimizer model.parameters lr is equal to 0.001, momentum is equal to 0.99, and weight decay is equal to 1e minus 5. And you also need a scheduler, which comes from here. Optim So I have a question. What are the parameters that these guys used? Insane. Wow. It's actually very good. These models are very good, actually. Anyways, num steps is equal to len train data batch size bullshit plus int len train data is not equal to batch size is not equal to 0. Then I need to also add 1, and then this entire things times and epochs. This is the total number of steps that you have, and what you do is you also need a multi-step. You need a multi-step LR. Perfect. So you have torch.tim multi-step LR optimizer, and milestones is well, for E in T range, we also need to import all these things. From TQDM import T range. Now for this thing is going to be just epochs, which is an epochs and epoch. What the fuck did I import? And p bar is equal to this, in which case we define a data loader is equal to a data loader. It's going to take in a data set which is train data set, train data. It's going to take the batch size of PS shuffle, if shuffle is equal to true, pin memory is equal to true. So this is your data set is equal to this thing, batch size is equal to this thing, pin memory is equal to this thing. Oh, it's already done. T range, zip DL T range per step, epoch step, T range this for D comma E in P bar. God damn it, man. save every 1000 steps. There's no accuracy. And then what we do is we have the logics and the loss for model. We perform model, not here, I mean just put it here, it's fine. Model dot train, we feed data to model. There's a difference here because this object returns self dot image only false. If so this thing is simply going to be list for x. Okay. This much, and mamma mia, we lost equal to lost mean gather from multiple GPUs. And what else do we have? Okay, so there's nothing else left. We do loss dot backward backprop, update the gradients, and then optimizer optim.step and lr scheduler.step. That's it, mate. That's it. And train losses dot append last dot item if gs and gs dot save every is equal to 0 self dot save checkpoint security path is equal to models dot vae dot t. Yeah, let's try to run this thing, except mul is equal to discrete, god damn it, discrete vae hdim is equal to 16 num layers is equal to 6. Unfortunately I can't do much about it. Num tokens is equal to 32, embedding them is equal to 32, print model. Hey, you know what, fuck this, you can have just 2 layers, that's fine, 4 layers. And trainer is equal to discrete weight trainer, then you have the model trainer dot train, and batch size 32, any parks 1, save every 1000. Cool. Let's try to run this thing. We'll know if there's some bugger shit. Python 3 discrete v8 apply. Touch.in.touch.often. Yeah. Here we are. Model dot parameters function is not iterable. Batch must contain tensors. Pure image. I think the transforms should actually be part of the dataset itself. And the difference is here. Tuple object has now 2. So far trend true. Must be after mapping, not list. God damn it, asshole. Cool, mate. We're dumbass because our loss keeps increasing. Oh, screw this. Alright, so this is 128. Number of layers is equal to 6. Number of tokens is 1024. We need the color palette of 1024. And the embedding dimension is equal to 256. GST echo dot ipynb this thing GST get add echo star dot ipy GST get that is good. No. Get reset head echo data slash is equal to dot get ignore just get address get commit add VAE trainer will it work? I don't think so. For some reason I think I fucked up with my Responded Dall-E baby. Get push this. It's going to work now. Cool. Now my machine is also ready. I need to install a bunch of things before I can actually start using it. Clone Dall-E baby cd Dall-E baby Encoder data. Oh, perfect. So we go here and discrete way.py, have this thing, a model. We probably should print what are the number of parameters in this model, which is done using this thing. Number of params is equal to this thing. Alright. How much memory did I assign this thing? Oh my god, it's what? 120 GB, it's fine. Python discrete way.py pip 3 pip install ein apps. I can't believe I'm getting faster internet here in India at my home than this douchebag is getting at his place. LOL. So 4.9 million parameter network, what the hell? What was the final configuration that we decided? (64 128) 64 128. Number of tokens is 1028. Now you're getting this. Now it's getting the speed. Oh boy, it's way faster than my home. $683. We're probably need to kill the system. God damn, it's 11 years ago. This data set was made 11 years ago. It stopped. Why did you stop? Are you crazy? Loss has hit NAND, which means I fucked up. 9702. KL-9702. Should probably also have a check on my NVIDIA. Why am I getting loss as 0? How do I check if something is NaN? If loss, if torch that is NaN, loss by default true. Oh, dot any and print loss v is equal to true, v is equal to false, v is equal to v, and I need to update torch is NaN. Jesus Christ, man. I also need to exit. If they then exit. Dumbass. So somewhere down the line, I'm an asshole who fucked up because the loss, instead of decreasing, is actually increasing. Man, I don't understand this kind of shit. I should be much smarter about it, but well, I'm not. I'm too stupid. Can I just use Atom? Does Atom work? I hope Atom works. Atom is nice. Atom is cute. Oh, yeah. what is even the utilization of this thing? So yeah, 3 GB, that's it. Well, it has to be less. I mean, we have to use this thing for our optimization. Let me just respond to someone on messages. Index 5000 is out of bounds for index with access 0. It's clearly talking about something here. Damn, it's on a GPU. Even this thing trains pretty fast even on a CPU. Not this big of a model, but still. The loss is now hovering somewhere around 0.67 and sometimes hits as low as 5. Now it's 65657, 6577. Did it save any model? Of course it did not save any model. Why? Because it's an asshole. Supposed to save model, asshole. Asshole. Well, it's always zero, so how the fuck is it going to actually save the model? Dumbass. Plus equals to 1. Well, that'll be 3. And print and save the end. F go GS and I'll also take with open model slash vae loss.txt as f dot write dot join float x for strx for x in train losses. This way we are going to save train losses as well, and we can later analyze in what case did I get the perfect or the lowest train loss. Yeah, it works. Cool, it works now. So now we simply copy paste the changes that we made here, except we need to fix this. Cool. Cool, mate. Cool. So we have a pretty rapidly decreasing loss. Now we are going to visualize the results, how it is actually working. From discrete import discrete VAE model. And I'll also load the parameters that I'm using for this model. Model.eval, model.load, static, import tarch.load, model slash, what is the minimum loss that we have got till now? BA 5000, map, yeah, fuck it, I got a pretty ton of decent GPU. We're also going to import pip install matplotlib import.plot as plt matplotlib inline, and from pil import image of car. No, let's just load an image from Zephyr itself. Zephyr train C equal to Zephyr train C00. Dot numpy plt.im show this thing. Dot permute 1, 2, 0. This thing is gonna give me. And if I remodel tarch.tensor img dot view dot permute 2 comma 0 comma 1 dot view my 1 cross image dot shape transposed. Oh fuck. I also need to, sometimes I'll also need the final output just out. Also need the final output which is out, and model is going to give me, god damn it, model is going to give me this, not this, comma out is equal to this. We'll need to restart these things. B img dot shape 32 33 3. img dot numpy detach dot numpy out. Man, I'm low-key scared right now. plt dot I am sure out. Dot mute 1 comma 2 comma 0. So you can see it's actually not learning anything. It didn't learn shit, asshole. One asshole. Should I try training with a larger learning rate? is trained for one epoch. Learning rate, let it be a very large learning rate. Maybe it learns this way. Asshole. Loss is larger than 1, which means it is learning something. 1000, what does it learn? Let's see. Black, amazing, asshole. $27. Holy shit. Image normalization, PyTorch. Zero point 0.5, 0.5, 0.5. Mean. New. Zero point 0.5, 0.5, 0.5. Now do we normalize it? Does it actually help? Transforms dot normalize five 0.5 and does this help? And will also increase the learning rate, decrease the learning rate to some actually usable value. You don't want e to the power 28. It ain't learning shit. So another thing that we are going to do is we are going to do something called set seed. This way we are going to force our models to have a fixed seed value. Set seed 4. Random. Import numpy as np. I should say that. Alright, now let's start experimenting with these values. Where is it? I haven't seen when you're actually training GANs, you would like to use a very traditional optimizer or momentum 0.9. It's not learning anything again. In fact, predicting the same shitty value all the time. Oh wait. It's a batch size. No, the batch size has to be much larger. The batch size here for training is going to be 512 samples at any given step. So scheduler commented, this commented. Optim is going to be Adam. Let's see now if it works. Again, it doesn't really help. VQA. This is what we want. Vector quantizer. Oh, this is fine. There's a residual block connection. You lying son of a bitch. You lying son of a bitch. He was a lying son of a bitch. We now know that he was a lying son of a bitch. God damn it. What is VQ loss? Sample loss function. Recons input VQ loss. VQ layer. Where is VQ layer? VQ layer is most likely this particular layer. commitment loss is equal to latent. Latents that permeate this. Flat latents. Compute L2 distance between latents and the embedding weight. Oh, wow. So apparently what we are doing is much stupider version of what these guys have already done. Should probably just copy their code. We'll cite them, people. Don't be assholes about it. We will cite them. Still not learning anything. So you know what I'm going to do is I am taking a break, and what I'm going to do is I'm going to go and grab some dinner. Then I am going to train I'm going to code up VAVQE, VQVAE, read a little bit more about the details, particularly how the training is supposed to happen. And then I'll train one model on the CIFAR dataset. We'll see how it goes then. I'm sleepy. You know what? Let's just end the stream here. I will restart this thing once I'm done with it. Alright, 3.34. It's basically the model didn't learn shit. See, it didn't learn shit. Yeah, let's just end this recording here, and I'm going to restart work on this thing after the break.